Last video we figured out what the projectile's maximum height is, and in this video we're going to find out what the projectile's range is, or rather its horizontal distance. So it's a safe bet to assume that one of the equations we're going to use is our horizontal displacement equation, which we know is equal to delta x is v naught cosine theta times time. And remember, this is true because there is no acceleration affecting the horizontal displacement because all the gravity is only vertical. It has no effect whatsoever on the horizontal, which is why we don't have a gt squared term like we do in our delta y equation. But this equation alone isn't going to be enough. So we're going to need some way to figure out at what time does the projectile have its maximum range. Because if we can do that, just like in the last video, we saw that if we solve for the time at which the projectile had its maximum height, we solved for that time and then plugged it into our delta y equation and gave us our answer. So we'll do the same thing here, except for this time we'll solve for the time at which the projectile is at its maximum horizontal displacement, and then again plug it back into our horizontal displacement equation, and it should yield us the maximum displacement. So let's think about what other equation we can use. Last time we used the vertical velocity equation, but that only worked because the vertical velocity was 0 when the height was maximum. The vertical velocity is not 0 when the range is the maximum because you can see the projectile is coming down and hitting the ground fairly hard. So it has vertical velocity in the negative direction. It also has a horizontal velocity, and again we wouldn't know what that is, but we do know that because it is moving forward. It has a constant horizontal velocity throughout the whole thing. So that's not really going to help us out that much. But let's think about our vertical displacement. What's unique about our vertical displacement at this point is that it's in the same exact place that it started, meaning that delta y, or I'm sorry, I meant vertical. I apologize if I said horizontal. Our vertical displacement is going to be equal to 0. So if we can figure out the time in which our vertical displacement is equal to 0, we would solve for the time that delta x is at its maximum, because that's the furthest that the projectile is going to go. So we could say, we know that delta y is equal to negative 1/2 gt squared plus v naught sine theta times time. And so now that we know that we're solving for when delta y equals 0, we have 0 equals negative 1/2 gt squared plus v naught sine theta t. Now, since this is a quadratic, because we have a t squared term here, we are going to get two values of t. And that should make sense, though, because if you think about it, there are two values for when delta y is equal to 0. But the first one is right at the beginning, right here. And so it would make sense that the time at which the first delta y equals 0 occurs is when t equals 0, and the second is sometime later. So it should be pretty easy to figure out which t we want to use. So again, this is a little bit of algebra, solving for quadratic. We can factor out a t. So we get 0 equals t times negative 1/2 gt plus v naught sine theta. So again, in solving a quadratic, we want to figure out when either this term is 0 or when this term is 0. Well, we know when this term is going to be 0. This term will be 0 when t is 0, and that made sense because as we already talked about it, the vertical displacement will be 0 when time equals 0 because it's starting on the ground. So this is going to be the time at which the delta y is equal to 0 and the horizontal displacement is at its maximum. So we want to solve for this time. So we can say that 0 equals negative 1/2 gt plus v naught sine theta. And a little bit more algebra. 1/2 gt equals v naught sine theta. And t is going to be equal to 2 v naught sine theta divided by g. So now that we've solved for the time at which our projectile has its maximum horizontal displacement, we simply want to plug that time into our delta x equation right here, and that will give us our maximum horizontal displacement. So we know that delta x, again I'll just repeat it down here, is equal to v naught cosine theta times time. And we're just going to plug this time that we solved for right here right into this t. So we say delta x is equal to v naught cosine theta times 2 v naught sine theta divided by g, because this is the time that we solved for. And again, a little bit of algebra and some rearranging yields our change in x is equal to 2 times v naught squared, because v naught times v naught, times cosine of theta times sine of theta, all over g. So this is the horizontal range at which for the particle is moving. Now I'm gonna clean this up a little bit because I think it's cooler if you clean it up a little bit, and that requires a little bit of trigonometric knowledge from pre-calculus. Because in pre-calculus you probably learned that sine of 2 theta is equal to cosine of theta times the sine of theta, and if you're unfamiliar with this, it is best you consult your either your calculus textbook or your pre-calculus textbook probably has this formula and the proof written down in it. If not, you're still confused about it, certainly feel free to see me and I'll explain where it comes from. So we can see that we have 2 cosine theta sine theta right here. Ignoring the v naught square, you can see it right here. So we can rewrite our horizontal displacement as v naught squared times the sine of 2 theta divided by g. So there you have it. We have now solved for our horizontal range in terms of v naught, theta, and g. And I'll rewrite the maximum height range. So I'll say, well, so I'll write delta x max, and over here I'll write delta y max is equal to, as we saw before, v naught squared sine squared theta over 2g. So these are our two equations that out of other equations we were able to derive. And I think this is one of the coolest parts of physics, is that we started everything with just knowing that our acceleration is equal to negative g, because it's facing downward. That's all we started with. And from that, we've proved these two seemingly complicated formulas out of just that one simple fact. And I think take a moment to revel in the awesomeness of that fact. That out of almost nothing, we were able to prove two very complicated formulas. But let's go a little bit further. And let's go a little further in saying, well, what is the optimum angle to fire a projectile so that its horizontal displacement is maximized? And looking at this equation right here, we know that the sine of anything, the maximum it could possibly be is 1, right? Because sine of anything could never equal 2 or 3 or 4. It could at most be 1. So we want to solve for it. In order to figure out when the horizontal range is going to be at its highest value, we want to figure out when we want to pick the theta that's going to make the sine of 2 theta equal to 1. And so we already know that sine of 90 degrees, or pi over 2 if you want to go in radians, but I'll say in degrees for now, is equal to 1. And we know, so therefore, you want to say sine of 2 theta, because that's what we have in there, is equal to 1. And we can say that's equal to sine of 90 degrees. And so we want 2 theta to equal 90. So if 2 theta equals 90, then theta simply divided by 2 equals 45. Which makes sense, because if you think about it, in order to maximize something's horizontal range, we should fire it at an angle that bisects the x-axis and the y-axis. So that would be right about here. This would be the optimum angle to fire to get our maximum horizontal distance. So that's fairly intuitive, but we've not only now is it we could have made that conjecture earlier, but we wouldn't have had anything to back it up. Now we have solid evidence to back that fact up. And if we want to know what that actual maximum range is in terms of v naught and g, well, we know that the sine of 2 theta is now going to be 1 because we fired it at 45 degrees. So we could say our extremely maximum range for any angle is going to be equal to v naught squared divided by g. So let's do the same thing with y. Again, we know that the maximum value of sine of theta is going to be 1. So therefore, the maximum value of sine squared of theta is also going to be 1, because 1 times 1 is 1. And as we already learned, and we already know that the angle that gives sine theta its maximum is 90. And unlike before, when we had 2 theta equals 90, right here we only have theta in here, which means that theta, the optimal angle to get our maximum height, is going to be 90 degrees. And again, that makes complete sense, because if we want something to have its height maximized, we want to divert all of its velocity to an upwards direction. So we want to shoot it straight up. So that way it'll have its maximum height. Because if we start shooting it at lower and lower angles, more of the initial velocity gets diverted to horizontal, which we want if we want to maximize the range, but we don't want if we want to maximize the height. So it's fair. Again, maybe it was fairly intuitive, but we have proven it. We've proven that if we want to maximize height, we launch it at an angle of 90 degrees. So if we want to find out what that actual height value is, again, we just plug in 90 degrees here, and we get sine squared of 90 equals 1. So our maximum y, so I should write max over here, regardless of the most firing at the most optimum angle, is going to be v naught squared divided by 2g. And these two results are fairly interesting, because this tells us that if fired at their optimum angles respectively, a projectile can go twice as far horizontally than it can vertically. And I don't know what situation where that sort of information would be useful, but let's say you wanted to, you had a cannon, you had something that fires bullets, or some sort of projectiles, maybe not bullets because that's dangerous, and you want to hit Bob, who's standing over here, and you want to know how fast you have to shoot the projectile out to hit Bob, but you don't want to alert Bob by taking trial and error shots at him. So maybe you could fire the projectile straight up, and then figure out, well, if this is 5 meters and he's 10 meters away, whatever velocity will make the cannon go 5 meters up will make the cannonball fire 10 meters and hit Bob, and he won't have known what was coming, because we didn't have to take trial and error shots at him. We could take trial and error shots straight up in the air. And I know that's a stretch, because that situation seems unlikely, but this is just an example of how we could use, the equations we've derived in everyday life. And I think I just think this stuff is so cool, guys. And hopefully you guys too see the true epicness of what we've just done. So see you next time.